A really important rule is called the conditional probability. And this is a situation where it's a probability of something happening given that something else has happened. So it's not a marginal probability. It's not just the probability of one thing by itself. It's the probability of one thing given another. For example, what is the probability of you passing given that you studied? You could study for your exam or you could not study for your exam. And then you could pass or you could not pass. Or you could pass or you could not pass. So you've got 4 outcomes. You studied and you passed. You studied and you did not pass. You didn't study and you passed. You didn't study and you did not pass. And so if I'm saying what is the probability that you passed, it would be the sum of those two. The 2 outcomes where you passed. Okay, why am I talking about that? Well, I want you guys to understand or have at least something to compare the conditional probability to. Because now I'm saying, what is the probability that you pass given that you studied? So I'm essentially saying, what would be right here? Given that you studied, what is the probability that you passed? What is the probability of that right there? It's not the same as this. These two are not the same. It's not like a coin flip. Because if you didn't study, the probability of you passing would be completely different. Right? So I'm asking the probability of you passing given that you studied. That's called a conditional probability. And the certain event, so the one that we know has happened, is called a condition. Okay, so if I'm saying what is the probability that you passed given that you studied, the you studied is the condition. It's certain. And I'm asking you the probability of you passing given that that has happened. The way you write the notation is A given B. And it's very important here, the order matters. Because whatever you put after the line, that's the certain condition. And whatever is before the line, that's the uncertain event that you're looking for. So if I'm saying, what is the probability that you passed given that you studied? Okay, forget all this A-B stuff. It basically means that I know you studied. You did study. That's not uncertain. You did study. What's uncertain is whether or not you passed, and I want to know the probability of that, okay? Now, as far as the formula goes, it's the intersection of the two divided by the total or the marginal of the one that is certain. So probability of A and B divided by probability of B. And again, the order here matters. The probability of A given B is not the same thing as the probability of B given A. The reason I'm saying that is because when it comes to all the other ones, it actually doesn't matter. When it comes to, say, intersections, this is equal to this because they're, the intersection of the two is the same. When it comes to unions, this does equal this, but not for conditional probabilities. Super important. The other thing that's important when it comes to conditional probabilities is just knowing that they're giving you one. And that's probably the biggest challenge in practice. In theory, it's okay, I get it. It's simple enough. But in practice, when you're reading questions, it's sometimes hard to see that they've given you a conditional probability. So I have a few key words that you should look for. The word given is a big one. So typically, whenever they say given something, whatever comes after that is the condition. But other ones would be if out of the, sometimes they'll say like X percentage of, whatever usually comes after these things, you should consider that it could be a conditional probability. Now, I'm not saying be robotic and just as soon as you see any of these words, just automatically say, oh, this conditional. But, these are big clues that you might be dealing with a conditional probability. I'll give you an example. If you study, what is the probability that you pass? It's the exact same thing as what I said here. If you study, so I'm telling you that you studied, So whatever came after the if, that was the condition. What is the probability that you passed? Out of the students who studied, what percentage of them passed? Okay? These are some clues that you're dealing potentially with a conditional probability. Okay, we'll see some examples of that a little bit later. Now, when two events are independent, then it means that the outcome of one does not affect the outcome of the other. Where the probability of A given B is the same thing as just the probability of A by itself. You see, the fact that B has happened didn't really change anything. I'll give you an example. If I flip a coin, the probability of it landing on tails is 50%, right? The probability of tails is 0.5. Well, what if I flip a second coin? What is the probability that the second one lands on tails, given that the first one also landed on tails? It's still 0.5 because they're completely independent. The outcome of the first one does not change the probability of the other one, and that's what independent means. Now, the multiplication rule for independent events is just the product of their two marginal probabilities. So the probability of both coins landing on tails would be 1/2 times 1/2. Times 1/2, which is 1/4. And if I go back to that first tree diagram we did, since these were independent events, the probability never changed. You saw the probability of getting the right answer stayed 1/4 every time because each, in this context, they were independent, right? If you get the first one right, it's not going to change the probability of you getting the next one right because you were guessing anyways. Now, it's not always the case. Other situations, like this one, they won't necessarily be the same. And let me just make some numbers up. Let's say there's an 80% chance you study and a 20% chance you don't study. Well, the probability that you pass, given that you studied, is probably really high. And the probability of not passing is probably pretty low. But if you didn't study, the probability of you passing is probably pretty low, let's say 20%, and the probability of you not passing is probably much higher. You see, these would be considered dependent events. Dependent, because the probability of you passing depends on whether or not you studied. So that's what independent means. Okay, let's do another exercise. So still with this MasterCard Amex example, the question here is find the proportion, which is, by the way, the same thing as saying find the probability. Okay, find the proportion of MasterCard holders who have Amex. This is a conditional probability. I'm basically saying, I'm telling you that out of the people who have MasterCards, what percentage of them have Amex as well? The important thing here is not trying to quickly solve the question. Making sure you really wrap your head around it is very important. Because you don't want to mix up which one is the condition. So look at it, break down the English. Find the proportion of MasterCard holders, right? So the MasterCard holders, this is your condition. I'm not asking you whether or not they have MasterCards. I'm telling you they have MasterCards. So I'm saying, what is the probability of somebody having an Amex given that they have MasterCards? And so you would then follow the formula. You would take the intersection over the one that is given, the one here. And we already have this, right? If I go back, we have the intersection. We had found it. It was 0.0883. 0.0883. And we had the total of MasterCard, which was 0.4417. It's 0.1999. Now, with a contingency table like this, you could actually solve this exact same probability using pretty much the same rule, but never actually finding probabilities. What I mean is, if you went to the intersection of MasterCard and Amex and took the 250, and then just took the total of MasterCard, which is 1250, that would give you 0.2, and is basically 0.2. The reason we didn't get 0.2 was just because of some rounding. Okay, so you can solve conditional probabilities using the actual probabilities, or if you have the units, you can do the same thing, as long as you're taking them from the same place, the intersection and then the total of the one that's given. Are the events having a MasterCard and having an Amex independent? Well, to answer this question, remember what independent means, where the probability of having an Amex, given that you have a MasterCard, should be equal to the probability of just having an Amex, where having a MasterCard does not actually change the probability of you having an Amex. That's what this means, right? That the probability of having an Amex, whether or not you have a MasterCard, is the same. So I would set this up this way. I would say, well, this, if I were to rewrite it as its notation, it would be this, which is what we just calculated, by the way. And I would compare it to this. So we know that the probability of A given M, we just found it, is 0.2. What's the probability of just Amex? Let's go back and see it. We had found that earlier. It was 0.1166, not at all the same thing. So they are not independent. They are not independent, which means the probability of having one changes if you have the other. The probability of one of the outcomes changes as a result of the other one. So that's how you test independence. Very simple, okay? Probability of A given M should equal the same thing as A. You could have also done M given A, but we know since we had this information, we were able to use it fairly easily.